Here we discuss factor models and using linear algebra to approximate coordinates relative to a basis. So we have the notion of a basis, and what we're saying is that we've got this vector RT plus 1 that we'd like to write with basis elements that form this matrix X. Remember, this matrix X is going to be our factors for whatever quantitative model you're using. Maybe price to earnings, maybe you have something involving a function of dividends, maybe you have some sales factor, maybe you have some type of measure of historic volatility or liquidity in the market. The Denali model uses many of these factors, and the basic idea is we'd like to find beta hat, which represents R. We'd like to find a beta hat, which is a representation of R relative to the X or the factor basis. Now, again, this is very difficult to do in general due to the high dimensionality of the return space. So typically you're going to have an epsilon here, an epsilon error term, and you won't be able to pick up the R exactly, but in a perfect world we could. Now, this is all great, and there are ways to test how close to a basis your factors are. And again, not all bases are created equal. You might have an orthonormal basis, which would be kind of the highlight of all bases, in that your F factors would be orthogonal to each other and have unit length. That's an orthonormal basis. But since this X will in general not be a square matrix, we can't invert it, so we can't pick up R directly with the coefficients on our basis elements beta. But if X has full rank, which is generally will be the case with these factor models, what will be invertible is X transpose X. It'll have full rank, and an inverse will exist. And if you think about taking this matrix equation and multiplying both sides by X transpose, one can get that a solution here to beta hat is this: X transpose X inverse, X transpose RT plus 1 will be beta hat. And this is called a solution to the normal equations. The normal equations. It also coincides with a least squares solution. So what this is we say, okay, our X beta hat is not going to be exactly the future return. And again, what this X hat beta hat means is a linear combination of factors is not going to perfectly equal this return. So there's an error term, but it can get close. We can approximate it with something. But what do we mean by close? Our measure of closeness, which is a natural measure, is going to be the sum of squared errors. And under that measure, which is a nice measure because if you're far off it penalizes a lot, and if you're very close it penalizes less than a linear penalization function. So having this sum of squared errors be your measure of closeness, this least squares solution is your best fit. And this is performed by regression. So the main idea of regression is you're orthogonally projecting downward. So you might have a vector here, u, and you might have here a vector, v. And what I'd like to do is project v onto u. So this vector here is known as the projection of v onto u. And that's the idea behind regression, is you're minimizing this sum of squares with these projection type vectors and these projection type matrices that are solved through the normal equations. And one can prove that these least squares solutions satisfy these normal equations by looking at the null space of your matrix X and things like that. But that's the basic idea. Now, what the least squares solution beta hat gives you is it gives you your best estimate beta 1 f1 plus beta 2 hat f2 hat vector. It gives you your best guess at a linear combination of factors from your factor model to get you as close as you can in the least square sense to the future return. Now in Denali's model, we have 37 of these factors in part of our model. Now they're not always used at the same time, depending on how close we think they are to representing a basis for the return space in that given time. So they can change on and off depending on different investors' views. But once we set up our 37-dimensional basis, or 30 or whatever it may be that quarter, we need to find the coefficients relative to that basis for each return in the space to forecast that future return. And a neat way to get an estimate for these coefficients, because again, this return, this may only be a basis for a subspace of the return space. So we just want to get close, and this notion of least squares regression can get us these coordinates for the returns relative to the factor basis. And that is why having a good basis of this for this return space, whose elements are these factors, and picking these factors is really the art. Then we use the statistics of regression analysis to interpret the coordinates relative to that basis. And I think we'll talk further about multivariate regression in another talk.